Okay, good day, everyone, and a very warm welcome to all of you joining us online. This is a Frontier Forum organized by the Smart Materials and Devices. We are honored to have Professor Gordy sharing his work on adaptive light management for energy conversion. I'm Jin Chen from Suzhou University, and I'm a youth editorial board member of the journal. And it is my great pleasure to be your host for today's forum. Before we begin the presentation, I would like to take a few minutes to introduce the Smart Materials and Devices. SMD was founded in 2024 as an international open access journal. SMD publishes quarterly and follows a single-blind peer review process. With the initial target impact factor over 4/7, the journal aims to establish itself a high-impact academic platform for research in smart materials and devices. We are pleased to share that there is no APC before 2029, and we will provide a free English edit. SMD also offers initiatives like annual Best Paper Awards, volunteer forums, and scholar interviews to improve the visibility of researchers. And please take a second to scan the QR codes on the screen to follow our journey on LinkedIn, X, and WeChat. Basically, SMD is a peer-reviewed open access journal providing a platform for research on smart materials and devices and their integration with AI. We welcome various types of high-quality submissions, including articles, reviews, perspectives, and the subject areas include smart materials, smart devices, to machine learning and AI for materials. Our editorial board is led by Professor Zhong Yongyuan from Nankai University, and together with 5 associate editors with expertise spans material chemistry, physics, and device engineering. To ensure the high academic quality, SMD is supported by an international editorial board. It's currently composed of leading scholars from diverse regions. We also organize a youth editorial board to promote the development of the journal. SMD continuously expands editorial team and welcomes outstanding scholars to join us. In addition to regular submissions, SMD actively organizes special issues around emerging research topics. You can check this link for more details about our special issues. Okay, this is a brief introduction to our journal. And back to our presentation, I would like to briefly introduce today's participants. Briefly about myself, I'm a member of Suzhou University, and I'm working on optical management of thin-film solar cells. Now it's my great pleasure to introduce our speaker, Professor Jake Gordy from Friedrich Alexander University, Erlangen-Nuremberg. Professor Gordy is a world-leading scientist in photophysics and nanomaterials. He has been named among one of the world's highly cited researchers and the world's top 2% scientists. We are also honored to join by our discussion guest, Professor Sascha Santos from University Mughal-e-Naz. Her research interests span functional organic materials, molecular electronics, and photoactive materials. And now the final quick tips. This forum is open for discussion. Please type your questions into the chat box at any time, or use the raise hand button during the discussion session to speak. Okay. Thank you for your attention, and please join me in welcoming Professor Gordy to sharing his research findings on the adaptive light management for energy conversion.
All right, then let me take over. Do you mind, let's say, like to get out of your sharing?
Yeah, I will stop my sharing. Okay.
Okay. Do my part. Okay. And we hope that it works out, does it? All right. So let me just briefly, oops, do one thing. Okay, all right. A very good morning from Erlangen, located in the midst of Europe. And it's a great pleasure to kind of share what we've been doing over the last, I'd say, 10 years in terms of smart materials, because that's been the main focus of today's, not only the journal, but also, let's say, like my talk. So I entitled my talk as Adaptive Light Management for Energy Conversion, and I greatly appreciate this opportunity to speak to you this morning, in particular to such a large crowd of people. All right, so what I'm gonna do is it's like, oops. All right, so what I got in mind is to share our approach with, first of all, looking at, let's say, like photons, and then how we manage those, meaning harvesting, funneling, transferring, and you would see examples later on. But if we do so, we got to notice that we're not necessarily constraining ourselves to the use of the visible light. In the visible light section, circling that here with my laser pointer being sort of somewhere between 300 and 800 nanometers. No. After all, we're going to go beyond that, particularly in the near IR. And I'm not emphasizing or advocating that we push it all the way to whatever 2000 nanometers and beyond. But still, and I'm going to dwell on that later on, that there's an important part that we're missing out. And the same is in the UV. So overall, we're going to like aiming at a more efficient usage of light across the entire spectrum. So I said once again, not only the visible part. But before going or jumping into details, let me give you a brief overview of what we've been interested in, let's say, like all along. At the forefront has been carbon, and it's still carbon. Talking about 60, talking about carbon nanotube. And eventually, likewise, nanographene or graphene, and also carbon dots. So with those nanocarbons in the background, so they're more or less utilizing us. Utilization of photon management, I already dwelt on that, in charge management. So we're talking about, let's say, like either up conversion, downshifting, upshifting, charge management. That's more in terms of electron transfer, and I will give you a few insight in that in a moment, because this is extremely important for a broader understanding of managing photons, because that charge management is something that we've been doing for many years. But rather than just managing them, meaning upshifting, downshifting, an important part is storing. So storing those light energies or the charges over minutes, hours, and even ultimately forever. What that has in a more recent trend, also giving us opportunities to look at information science. So it's not only monitoring charges and photons, as I said also. Okay, if you look at that now, a brief look back into history. So this is in 1954. So that's the first installed solar panel at Bell Labs. You see, it's pretty much, let's say, like whatever, 3" by 5" at max. We're not talking about efficiencies at all, but it certainly was a first demonstrator on how you convert light into electricity. And that's particularly for the audience from China. This is in Midong Solar Park. This is a solar farm that produces on the order of tens of gigabytes annually. But there's always a but associated with that. It might not be coming straight out of that picture, but if you look at the entire solar park that has kind of the size of the entire city of Chicago in the United States. So there have been pros and cons associated with that. What I'm dwelling not only on 2024, but since 2023, worldwide, the energy production by conversion of sunlight into electricity is reaching terawatts. That's what I put up here. And at the turn of the century, that used to be the main challenge. And I'm not advocating 8 terawatts as it used to be, or currently in the range of 20, or even extrapolating into whatever 40 or 50 within the next 20 to 30 years to come. Nevertheless, terawatts, that's the important part. Okay, before I'm gonna go diving into, let's say, like what the main focus is of today, I wanna give you a brief introduction, and please take it more like an introduction on how we can, at least on a molecular basis, considering dealing with charges in particular. What I have here is a donor acceptor structure. So the porphyrin that you see here on the left-hand side, mimicking chlorophyll, what we typically see in nature. So it's an artificial surrogate, you might say so. And I did mention before that we were much interested for many, many years in fullerenes as electron acceptors. And these electron, well, C60 or C60 derivatives, they're replacing the quinones in nature. So rather than having a chlorophyll and a quinone, we have a zinc porphyrin or porphyrin in general, metalloporphyrin and a fullerene. The important factors, you can basically erase that immediately from your memory, what I'm talking about here, the porphyrin and the C60, but it's more about the linkage. So we have an imide linkage that is enabling kind of rigidity. And when we talk about that support is supported here by, at that time, picosecond trends in absorption spectroscopy. Spectroscopically, if you photoexciting the, let's say like the porphyrin or the chromophore, let's keep it on that level, we're dealing with an electron transfer because this is an excited state electron donor that is regulated exclusively by that linkage. So that will be the important part of my introduction over the next few slides. Anyway, here we look at time delays between picoseconds. So I'm putting up here arbitrary minus 300. This is kind of, let's say, like baseline offsetting. But the point is that what we follow in these trends and absorption measurements as a function of time, so that's what you see here on that axis, we're looking at differential absorption changes. So we're taking absorption spectra of excited states as a function of wavelength. And as one sees here in this slicing, that as time evolves, we see broad absorptions here between 500 and 600 nanometers. That's what you see here on the X scale, and likewise in the IR. So we can easily ascribe that, now at least in hindsight, to an intramolecular charge separation. Intramolecular, because everything is controlled, once again, by that linkage that are highlighted here in gray. But one noticed that that's not ultimately stable, and it shouldn't be, because at longer time delays, you see both of these signatures fading away. And that's the charge recombination. So you localizing upon excitation and charge separation the electron on the electron accepting fullerene, and the hole, so that's the radical cation, on the zinc porphyrin. So with time, that also recombines. That's important because what this enables us, first of all, a very fundamental insight. And the fundamental insight is when you're going back to the natural photosynthetic reaction center, where you have a whole bunch of chlorophylls that funneling light on basically the laser pointer, reaching a special pair. In that special pair, one sees two chlorophylls not covalently linked, but they're pushed together by the protein matrix. Bear in mind, these are two. I will come back to that later on. So the proposal is that light kind of reaches that special pair, and there's an incredibly fast symmetry breaking charge transfer. I'm not saying charge separation, but symmetry breaking means that you have two identical chromophores, and they're still, rather than being localized, we delocalizing charges. And from there on, electrons, not charges, electrons, have been transferred to pheophytin. That's what you see down here. That's a magnesium-free chlorophyll. There's a quinone and there's another quinone. So what I'm trying to tell you is that all these forward electron transfer reactions, once again, special pair to pheophytin, from pheophytin to quinone A, and from quinone A to quinone B, or B and A, vice versa. These are all highlighted in green. Each of them competing with a recombination, as I was showing you before, for instance, in blue. What Mother Nature has designed is that the forward reactions are fast, and they're faster than the back reactions. And I can go back to what each of us have been taught back in kinetics. If you have competing reactions, the one that outperforms is the one that is faster. So this is by design. All right, now I'm going to our 60 zinc porphyrin system. And what I'm plotting you here is the driving force. That's the same kind of mechanistic energy diagram. So that's the excited state, that's a charge separation, a charge separated state, beg your pardon, and that's then indicating the charge recombination. The differences here between these lines is the driving force. That's what I'm putting here as a free energy driving force as minus delta G for the electron transfer in the electron volt. And we see that this increases from the left to the right. Now, interestingly, is the fact that the driving force for the charge separation is very small, or small, and smaller than that for the charge recombination. So intuitively, one would expect that if the driving force for the charge recombination is larger, it should be faster. Here, you're looking at the rate constants, and you see the reversed. Reversed is that the charge separation, although happening at a much smaller and ergonic driving force, is faster, than the charge recombination. So that's what was the 60 porphyrin system. And it's the same what we see in nature. I want to take that a little further because I want to just take that and without this intermediate, I'm not saying long-lived, but at least ability to store charges, electrons and holes, we can monitor process in time. How do we do that? Well, first of all, we want to push the time scale a little longer, and bear with me giving you that example here in details, where we have now 3 components. We have the zinc porphyrin and the C60 that I was telling you before, and we're interfacing the two with another porphyrin that I'm highlighting here in gray, and that is without a metal. There's a good choice for that free base porphyrin because this is, let's say, like not the highest lying, but once we separating charges. In analogy, what I've shown you before, so the electron is on C60, the hole is on the free base porphyrin. As I said, there's a design issue, or not issue, but an aspect, namely that the porphyrin is a stronger donor as zinc porphyrin than the free base. And if it's a stronger donor, it can easily accept that hole or the positive charge that I'm storing here in my first step. So I'm kind of getting, like in nature, this short-range electron transfer, or let's say like hole transfer, first to the free base and then to the zinc porphyrin. So this is hypothetical. Now, if I'm looking at a kinetic argument, where I'm looking at the rate constants, so this is 10 to the 9 per second, intramolecular. So these are unimolecular, concentration independent, versus 10 to the 6 for the charge recombination. We're realizing that this is what I said before in the natural photosynthetic reaction center. The forward hole transfer is faster than the back transfer. And that's critical because now we can look at, let's say, like the long range back electron transfer, meaning the long range back electron transfer is by tunneling. I don't want to confirm this, but you have to take my word for that. And I could, if you ask, give you plenty and ample of evidence for it. But I'm looking at that, and what drives these electron tunneling is the molecular backbone between the free base and the C60. I'm putting up here an electron affinity mapping that indicates kind of the flow. Of course, this is on electrons, and you have to take the corresponding color imaging, meaning whatever is shown here in red or orange, I am kind of looking from the zinc porphyrin all the way across to the C60. And this is very heterogeneous. And I'm picking up on that heterogeneous in a second, because This is kind of the hard piece of what you should take home, not from my presentation, but from that introduction that I'm trying really to convey. Because what I'm doing here is I'm plotting the distances between the zinc porphyrin in the first case, here and between the zinc porphyrin in the second, and also between the ferrocene. And here you see the corresponding values, 1, 2, and 3. These are the rate constants for the charge recombination. And what we can do with the slope, if I'm taking all these 3 data points, I can look at kind of the damping factor. And the damping factor gives me my attenuation over larger distances on how good or how bad electrons or holes are being not transformed, but transported. And with that 0.6 per angstrom, this is really, 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 really poor. This is very close to vacuum. Vacuum is roughly 1 per angstrom. And if I'm taking that indication of that it's as poor as vacuum, I'm going to relate back to what pretty much everyone here in the audience should know from STM. So I'm talking about tunneling microscopy. And what is imperative is that you put the tip as close to the surface or to your object that you're probing, because you're tunneling electrons through vacuum. If you're too far off, you will never see any tunneling current. So this is as bad as it is. Now I'm turning your attention to a very different approach. That approach is here a pi-conjugated system of a phenylene-vinylene. So you're noticing that there are alternating double bonds, and what I can do by implementing several of these repeat units, I can change the separation and the distance. And that's what I've done here on the left-hand side, where I'm plotting now, once again, the rate constants as a function of distance. All right, so you notice immediately, here I have a very steep slope. Here I got literally no slope at all. And that's not cheating, because the values are exactly here on the rate constant. So this is between 25 and 0. That's between 25 and 0, and also the distances. So we're not comparing apple and oranges. We're comparing exactly the same fact. I take that and deriving from that, let's say, like nearly negligible slope, the damping factor. This is 0.01. Note the difference. And my message for you is what is imperative. It's not only what matters between A and B and how that impacts rates and electronic coupling. No, we prove it. Okay, once again, electron affinity mapping, you see that this is very homogeneous. But no, look, before jumping into the real topic of today's talk, the impact that it makes. In that system where I have a very poor kind of conduction of charges, the lifetime between the ferrocene or the ferrocenium, this is the one electron oxidized, and the C60 radical anion, is nearly a second. Very poor medium to transport. If I'm switching to the phenylene-vinylene system, at nearly the same separation, the lifetime is only a microsecond. You see what the impact is. This is humongous. All right, so I hope that I haven't bored you, but that's critical for what I'm going to talk about in the following. Now, let me further motivate you about using the entire range of the solar spectrum. I'm providing here you with 2 examples from my lab, from our lab here, where we used a photocatalytic approach. These are perylene-based diamides. They're absorbing between, depending on substituents, between 500 and 600 nanometers. This is max. But we're using only that fraction of the solar light. And what we can do is with PDI, we can activate a water oxidizing catalyst, and that then drives the O2 evolution from water. Emphasis on PDI. The right example is an iridium MLCT, a metal to ligand charge transfer complex. So it's a transition metal complex. I highlighted this a little bit, it's like because this is yellowish, orangish absorbing, meaning 350 nanometers max. But what we've done here photocatalytically, we looked at triplet energy transfer to disulfides. And once you have that disulfide in its triplet excited state, you're inducing a bond cleavage. So you're ending up with tile radicals that can recombine, or if you further quench them, and that's what we've done in collaboration with the group in Münster, you can, for example, use them for the methionine production. So this is photocatalysis. If you look at photovoltaics, it's a very similar aspect. I did mention that, yeah, here is a heterojunction for silicon N and P type. See, this is here P, this is N doped. You have the zone depletion layer. Once you interface the P and N type of, let's say, like your silicon doped with element 3 or 5, on what the maximum efficiency, theoretical efficiency, is 33%. First of all, you wonder what happens to the remaining 65. Why is it only 33%? Well, as I said before, if we use UV light excitation, we have thermalization losses. So it's not that you're converting every single charged carrier that you might produce into free charged carriers that you can extract. No, you lose them because of thermalization. And the consequence is you're heating up the device. And that's what actually happens. I mean, they're operating at 80, 90, 100 degrees centigrade rather than at room temperature. When we turn to the near infrared, well, the photons are simply insufficient in terms of energy to excite across the band gap. And that's what really is the bottleneck. Sure, I mean, we're using a much broader section than on the PDI-driven water oxidizing catalysis, and likewise on the iridium-induced triplet sensitization, but we're dealing with significant losses. So here's what I'm going to talk, I mean, that's the main focus of today's talk, that I'm going to use these blue and red photons, I want to use them, and push the efficiency of a single junction solar cell that I described in the previous slide to 33%.
Recording stopped.
Push that to 39% and beyond. We're going to do this on a molecular level. So we're not talking about multiple exciton generation based on small band gap lead sulfide or lead selenide nanoparticles or even materials, but rather on acenes. In the mechanism that I want to just put up, this is what I've taken from the literature, but I want to jump into that and give you more insights on it, on how you're converting a singular state in two triplets. So by that conversion, so in the down conversion of cell fission on the molecular level, you're generating up to 200% triplet quantum yields. Bear this in mind. These are triplet quantum yields relative
Recording
to the
in
same.
progress.
On the up conversion, so when we're talking about using photons that are really far in the red, it's basically the reverse process where you're combining two of those low energy triplets into one singlet. Here, you can't go to 200%. That's impossible. 11% is when you're looking, let's say, like spin statistics. Spin recycling, you probably can push it to 50%. Nevertheless, these photons would not be used at all. All right, so what I'm going to do is I want to now tell you what was known before we started with our work, and that was in the solid state. So acenes, as I said, this is at the forefront here, pentacene, and because of repulsive and attractive interaction, the solid state, or in the solid state, one sees this herringbone structure. And 3.7 angstrom is the separation between these pentacenes. So the 3.7 angstrom now gives me what I was giving you in the introduction, my electronic coupling on how they should interact. That's going to be critical. This is in the solid state. On the left-hand side, I'd like to draw your attention to experiments that were not done by us, by two photo emission studies, where you're photo-exciting these pentasene, sorry. That's around 650 nanometer. And then once you have it in the excited state, you're coming in with a high energetic burst and you photoionizing the state. And what you're measuring, similar like in UPS and XPS, you're measuring the kinetic energy of that ejected electron as a function of time. And this is the interpretation early on. So that's picosecond. You're seeing a single excited state form and that two consequent states populated. Let me just do this here on the right-hand side, because this is a lot more illustrative as simply the raw data. Once again, you have a single excited state and you're only exciting one per unit area, and you can transform that single excited state, this is the proposal, into two triplets. Note that two electrons up, spin up, two down. So that's a triplet and that's a triplet. If I merge the two, it's an overall singlet. That's important because what it does now helps, it renders this process, so the conversion of one singlet in two triplets with an overall singlet configuration spin allowed. And that helps to outcompete many, many other processes, as you will see in a second. And later on, at least in the solid state, the proposal is there's spin decoherence and the triplets can freely diffuse. All right, so that's in the solid state. We're looking at solution experiments. All what I was giving you an introduction are done in solutions of solvents of different polarity at very low dilute concentration. So it's all intramolecular. Now, if I'm taking that same example of pentasenes, I cannot do this in solution with regular pentasene because they're extremely unstable, particularly under light. And that has to do with the 6 and 13 positions. Please ignore the fact that I'm putting here some substituents, but the 6 and 13 positions, because if I'm drawing the maximum number, or let's say like the maximum aromatic units, I'm going to consider this end and that end. So that's the class sextet, and I'm ending up with a kind of an issue drawing, let's say like an aromatic character in the central ring. And that adds an open shell or a diabatic alloy character at 6 and 13. This is why I can't use pentasene per se in solution. But if I'm functionalizing them, and that has been done here by my collaborator and very good personal friend, Wojtek Queisser, at the University of Alberta in Edmonton, they're more or less stable, but they're stable enough. So that's how I could do this in solution. But if I'm taking two monomers, then I'm relying on diffusion control processes. And now here's my point. Other than relying on diffusion, we're going to link them. Now, that's why I'm giving you that introduction in the first part, that by choosing a linker, and this is a metaphenyline, I can tune interactions, not between an electron donor and acceptor, like it's a 60 and a porphyrin or any other electron donating entity chromophore. No, between two pentasenes. So that's the meta linkage. And the proposal is, when we started with taking these, now all these dynamics become intramolecular. So that's why I put here ISF for intramolecular singlet fission, then to form triplets. These are important reference experiments because if I want to do that, meaning transforming one singlet into triplets in that particular conjugate or dimer, I have to make sure that the thermodynamics are right. The thermodynamics, meaning I'm looking at the singlet excited state, absorption and fluorescence, and the triplet, that's low temperature phosphorescence at 0.77, 1.84 for the singlet. And you're noticing if I'm taking two of those, I'm ending up rendering the process endergonic. So the offset is my driving force. And here are some data on it. These are now not the picoseconds experiments that I showed you at the very beginning, but rather our femtosecond. So these are 150 femtoseconds, and I want to explain to you what I'm showing you here. So we're looking at wavelengths between 400, so we're focusing on the visible range, 400 all the way to 1200 nanometers. This is a function of time. early on. So this is logarithmic. Down here, that's the excitation. And then we're following as the experiments progress as a function of time, differential absorption changes. And the way that we typically plot them is in orange, yellow, and red. These are excited state absorption. Excited state absorption means that the change, let's say like the absorptions in the excited state are stronger than in the ground state. You can also look at blue and dark blue and purplish. These are ground state bleach or stimulated emission, where the reverse happens, that in the excited state, the absorption is weaker than in the ground state. So now what I want to just show you is, after explaining and how we're plotting that, is early on you see one species form and there's a second one. Doesn't matter whether you're following the red and the blue. And if I'm taking here time window roughly, that's about 200 picoseconds. These are here on the left-hand side, simply two choices, time absorption profiles. Taking here, where I'm putting the laser pointer, roughly 510 nanometers. And the second one is at 611, that's ground state bleach. And no matter what you do, you see the same maximum population at 200 nanometers. And if I'm taking crosscuts, not from bottom to top, but from left to right, as we show here, we can confirm that within 200 picoseconds you form the triplets. Before going any further, I have to tell you that if I'm only looking at a monomer, so one of those, nothing else, the lifetime of the single excited state is 10 nanoseconds. 10 nanoseconds versus 200 picoseconds or 0.2 nanoseconds, that shows you that the process that we're proposing, namely the triplet formation, is much, much faster than the intrinsic decay. If I'm doing a spectral deconvolution, actually I'm ending up with 3 states. So blue and orange, so this is what I've taken you from that solid state where everything was incredibly fast. This is the singlet, and this is the singlet correlated triplet pair. There's an intermediate state. We cannot deny that, at least when we're deconvoluting the data. Question is, what is the nature of that intermediate state? And I gotta go back to what I said about the special pair. I have, in a special pair, V-shaped chlorophylls. In our current case, I have 2 pentascenes that are covalently linked by the phenylene bridge. And this is symmetry breaking charge transfer, where I'm delocalizing electron density. One is partially reduced, one is partially oxidized. But I'm coming back to that later on. Now, notable is, and I'm going to go back a little bit here towards our femtosecond measurements, that towards the end, so here 5 nanoseconds, nothing left. So apparently I formed these triplets incredibly fast, but their decay likewise very, very, very quickly. And that is what I was showing you early on. So what I can conclude here, rather than looking at spin decoherence and all the other processes that I will elucidate later on in an independent consideration, I have only triplet annihilation, but to the ground state, nothing else. Okay, what is the nature here? And the nature of that intermediate state, I already put up my symmetry breaking charge transfer, once again, delta minus delta plus, but it's in a super exchange mechanism that we're proposing. It's a new quantum state. And that new quantum state, so here with a wave function, is a wave function mixing of 3 components. 3 components, meaning I have mixing of my singlet. Then the second component that mixes in that new quantum state is my symmetry breaking charge transfer. And the third state is the triplet. And the wave function mixing, C1, C2, and C3, depends in this instant on solvent polarity. I'll give you one example, and if I go to more polar, I'm mixing in more triplets. And I can verify this all spectroscopically. So that's interaction in the matter. But it's only an excited state. We have no handle to follow this, let's say like in ground state, let's say like electron absorption or electrochemistry. No way. I mean, they behave in the matter because of a rather poor coupling as nearly two independent chromophores. If I'm changing from a meta to a para, certainly I have much better conjugation between one and the other, and we do know this from electron transfer. With that, I can now monitor on how these two individual pentacene molecules interact with each other. What I have in mind is simply configurational changes or rotameres. One that I'm proposing is here in a coplanar orientation, and then on top of it, anything that rotates out of coplanarity. And here are not on the paraphenylene, but on a bisacetylene computed or calculated spectra. Once again, for a coplanar and an off-planar. And what we see in the coplanar, I'm seeing such strong mixing that I have what we know from chemistry as a Jahn-Teller distortion, where I have two degenerate states, and I'm lifting the degeneracy, lowering one in energy, and raising the other one. And this is the lower one, and this is the higher. Interesting is the fact, once I'm rotating, as I said, these are calculated computed spectra. If I'm getting out of that coplanarity, I'm losing the splitting. So let's say like in a solid state, consider this Davidoff splitting, and I go back to two individual molecules, pentacenes. You might say they're orthogonal to each other. I don't want to really dwell on the fact that they're fully orthogonal. My point is they're not coplanar anymore. And if I hit that, and I can do that as a function of time, no, my dynamics become super fast, and I'm changing the mechanism. So I mentioned the super exchange in the previous with a new quantum state as an intermediate, as a real intermediate. Here, I'm forming the triplet in a coherent fashion. So right away, and they're incredibly fast decaying within 10 picoseconds. If I would now propose that quantum state, which literally doesn't exist, I don't mix my charge transfer, and no matter what I have, is that it remains independent. From a photochemist perspective, and not necessarily from new quantum states, I can look at, let's say, like diabatic and adiabatic scenarios. A diabatic for my meta, where I'm taking my initial state, the singlet, the final state is the singlet correlated triplet pair, and the state that I'm mixing in, for example, with the charge transfer, I can tune its position by solvent polarity. If I turn to the super exchange, if I'm going to a coherent mechanism, so an adiabatic, no matter what, even if I'm proposing it, I can never lower that energy enough to kind of interfere between those two states. I got a little bit of an activation barrier, but one could consider that electrons linger here around, and all what it takes is a little bit of an extra kick, and they go over that activation barrier. So that's the first part. The second part goes back to my introduction. The introduction, I've given you many different spacers, and the nature of this spacer determines my electronic coupling at the same distances. Remember that in one case, I had a lifetime of a second or 0.38 seconds. In the other instance, at the same distance, the lifetime was not even a microsecond. So how to do that? That's my conclusion here. And the question is, of course, dwelling on the fate of that singlet correlated triplet pair. How about if I replace that conjugated matter with an adamantal? In an adamantal, we have overall the same number of carbon bonds between that edge and that edge. Okay, here, there. The distance, 6.9 angstrom, is likewise the same, but in the adamantal, I have only saturated carbon atoms, while here I have that meta linkage. So what I would expect is by transforming from something that is conjugated and saturated, I'm slowing down dynamics. We do know that from electron transfer, and whole and below, if I'm now looking at my heat maps, I see the triplets formed after 2000 picoseconds. Remember, so that's for the adamantium, but what I wanted you to remember or reconsider, for the metaphenylene, it was 200 picoseconds, 1 order of magnitude slower or faster, depending on from which perspective you're looking at it. Moreover, here is the triplet. It's very slowly decaying. In the other instance, it was already done and out of the game at that particular time scale. Can we follow this? Because this is 5.5 nanoseconds. Yeah, we can, but we have to turn to a different setup, not in terms of excitation, still 150 films a second, but the white light generation. That's a white light laser, and we can go up to 500 microseconds. But this setup enables us to follow the triplet that we see here at 510 nanometers, and we see 1, 2, 3 components. They're all intrinsic absorption measurements the same. This is room temperature. If I do that at 105K, same thing. It's a little more smeared out. There are activation barriers involved. I can do that at 7K. I can do that at 5K. It's all exactly the same. Question is, why did we do that temperature dependence all the way to 77K and 5K is to do transient EPR. And what I'm going to do is here with the transient EPR, here different time delays on the nanosecond scale. So I have to emphasize that at least for regular transient EPR, the time resolution is 100 nanoseconds, and you go beyond that. So going beyond that enables me to detect the second and the third, not the first. The first is a singlet correlated triplet pair. There's no doubt about it, because it's the only way that these have been formed and compete, because it's overall singlet configuration. I want to pick up the second and the third. And the third is the easiest. The third is the gray spectrum that you see here in the transient EPR. This is just a triplet, an independent triplet. That's important. In black, that's the EPR signature in terms of absorption, emission, and so on and so forth of the second. And if I'm taking that signature of absorptive and emissive modes, because of, let's say, like the splitting that you're inducing at that particular magnetic field, and that we are resonant with that microwave field, then I can come up with two conclusions. Either it's a triplet that originated from a charge separated, but when I'm talking about a charge separated, I'm talking about a full electron on one and a full hole on the other. I was talking about a charge transfer. That's a partial delocalization. So that leaves the explanation from kidnaps, so chemical-induced dynamic spin polarization, out of the question. The other explanation, it's a quintet. And wait a minute. Quintet. Now, here's the point. That's my singlet configuration. 2 up, 2 down. No, a quintet would be all up or all down. So that's going from a low spin to a high spin. And then after all, I have the spin decoherence by which I'm forming 2 independent triplets. So that's the conclusion out of this investigation of my adamantium, that I have this quantum state, and in that formation via the quantum state as an intermediate, I can talk about electronic and vibrational decoherence because of the time scale, and that's the spin decoherence in the second part. First part is spin allowed, the second part is spin forbidden. That's from a singlet to a quintet. And that's actually the bottleneck. If you look at quantum yields, that's 188, or let's say like 190%, not 200%. In the second part, in the spin forbidden, it's 72%. And what drives the low conversion is the J coupling versus decoupling. J coupling is the true bond coupling between the two spins. If they're too strongly coupled, I will never have in my precession as a function of time any different field. So they're all remaining with the same precession speed or rate, and I never transform or go into a quintet. D is, let's say, like the through space. I come back to that later on. And I can also come up, let's say, like with another aspect that is really, really important. Here I'm drawing now my singlet and the quintet. The triplet is not formed at all because of spin selection rules. If I now look at the say like the coupling, once again, becoming decisive by either separation, but we have not changed the separation, but a conjugated versus a saturated, and I'm drawing the and spin mixing, then I'm lifting the degeneracy, because typically all these three should be isoenergetic. But now coupling induces different gaps between the singlet and the quintet. These are my important parameters for the spin flip, and that where the J coupling is counterintuitive. If I now go what I've shown you, where I have no triplet decoherence at all, rather than triplet annihilation, it's so strong, the exchange limit, that my gap between quintet and singlet is so huge that I'm not able to overcome that no matter at what temperature. So the quintet, after all, becomes a gatekeeper for the second part of singlet fission. It's not the first, meaning the singlet correlated triplet pair formation, but the quintet and then the spin decoherence. And also, let's say like the bicycloctet. The potential of this is 39%. But if I'm going to utilize that potential, I have to think what I'm going to do with my triplets. Because, well, if I'm forming them, no matter what, singlet, quintet, or uncorrelated triplets, I have to consider, first of all, their low energy. The quantum yields, I don't care at the moment. I shown you in the beginning by low temperature phosphorescence measurements that the triplet energies are only 0.8 electron volt. That's not much. Now, what we've done is, this is one example, and I believe, let's say, like for the future, this is probably the most important aspect, synchronizing the electron donation, because pentascenes or acenes in general tend to be very strong electron donors rather than acceptors. So synchronizing means that I can do this only interfacially. And interfacially, this is a monomer with, let's say, like a carboxylic acid here on the linker. I can graft them to metal oxides, N-type, zinc oxide, titanium oxide, and so on and so forth. On the dimer, it's a little bit of more of a tricky, because at least when I place the carboxylic or acid directly here in that 135, or relatively speaking, in that position, I'm not able to put that on titanium dioxide. This is something that we did not figured out why it never happened, but there was no colorization even after several times of potential uptake. But it did work out with zinc oxide. Now, let's look at the monomer that certainly injects into the conduction band of zinc oxide from the singlet excited state. That's what I'm drawing you here. On my dimer, now what I'm gonna be is I'm gonna be fast. I need to be fast enough for my singlet fission, meaning that I form a correlated triplet pair of no matter what spin configuration, that should be faster than the intersystem crossing, or even the injection from the singlet. And we've done that, let's say, like by transient absorption measurements, that indeed that we had first the singlet fission and then the electron injection. That's 130%, but that is not happening with zinc oxide, no way. Because, as I said, the singlet, an energy, let's say roughly 2 electron volt, can easily inject into zinc oxide. Triplets with half of energy cannot inject into the conduction band. The conduction bands are simply too high. I can lower, however, that conduction band of zinc oxide by replacing zinc with indium. And if I end up with 60% indium, so replacement, not doping, and 40% zinc, I'm lowering it sufficiently enough that it can inject. And that's what the data is here. That's 130%. But again, this is very, very complicated. The alternative approach would be sensitization, that I'm taking these triplet excited states that I'm forming here. This is for pentacene, doesn't matter. This is, let's say, like only a mimic, the dimers, of course. That's kind of the energy. So what should I sensitize? If I'm taking a silicon solar cell, I cannot, because the onset of absorption is roughly at 1.12 electron volt, and the triplet is too low in energy. So that's insufficient. I can do this with tetracene, so the smaller cousin of the pentacene, and that triplet is 1.2 electron volt. So that can inject into silicon with an onset of 1.12 electron. There's always a but, as I said before. If I'm taking 2 of those, I'm ending up with 2.4 electron volt. And if I'm taking 2.4 electron volt, this is the same as the singlet. So I'm dealing here with identical energetic levels. Sure, in the solid state, that process with the driving force, delta G as a free Gibbs energy is 0. But if I'm breaking it down into enthalpic and entropic, it's not enthalpically driven, it's entropically driven because I'm converting 1 into 2. That certainly has a positive delta S. But no matter what, and it has been shown, but no matter what, I'm ending up with, let's say, forward and back reaction. The forward meaning singlet fission, and the back reaction is the up conversion that I'm recycling my singlets. All right, here's insights in it. So it looks like what I've done before, but this is a tetracene, not a pentacene. Remember, the driving force is nearly 0, and that's why everything becomes slowed down all the way to the uncorrelated triplet pair. That's the mechanism that I concluded where we stopped for pentacene. Remember, that was triplet annihilation because of simply the gap to the quintet too high, and it will not being populated, but the annihilation outcompetes the quintet formation. That's the entire process for tetracene all the way to the uncorrelated triplet pair. The question was at that, how about quantum for any of those? So you remember that I've shown you, at least for the elemental, I've given you triplet quantum yields for pentacenes, and this is relatively straightforward to detect because we can look spectroscopically at the ground state bleach because there's no overlap with excited state absorption, straightforward, and these are absolutely accurate numbers. For tetracene, it's a mess. You can't do that spectroscopically. But then I thought, okay, how about if we use, because of 1.2 electron volt here, the triple excited state energy, that should be sufficient for the quantum Lie determination to be quenched with triplet oxygen, and then we measure singlet oxygen with its emission at 1260. Well, we did so. And we started our experiments, and that was very, very surprising with the fluorescence. This is the monomer in argon, 10 nanoseconds, so very similar lifetime, and it's nearly quantitative by which the singlet converts to the ground state because there's no triplet formed. If I'm admitting oxygen, it's a little faster, collisional deactivation, but still one component, 10 nanoseconds. Let me just remind you on that in the monomer. Now, if I go in argon, so in the absence of oxygen, to the dimer, all of a sudden the lifetime is hundreds of nanoseconds. This is weird. And second, I see a very fast component, I see an intermediate component, I see a slow component. So 3 components, the longest lifetime reaching into the hundreds of nanoseconds. And third, if I add oxygen, it's all done. These are experiments with singlet excited states. Yeah, we're looking at the fluorescence and oxygen is triplet. These were single wavelength TCSP, single photon counting measurements. We figured, okay, maybe there's something fishy and wrong with that. So we turned to, let's say, like transient emission spectroscopy. So we're recording the entire fluorescence or emission spectrum as a function of time on this time resolution scale of nanoseconds. So you see, it's pretty much the same. We deconvolute the data, 3 components. And it should be 3 components because that's what we see on one wavelength. And reassuring is that if we deconvolute the entire spectrum, we get the same 3 lifetimes because the values are also the same. And overall, all 3 components show the same fluorescence. So what we're doing here is we're upconverting. We're upconverting, and we have 3 components that contribute to the upconverted fluorescence. It starts with the singlet correlated triplet pair. This is the long 100 nanosecond lived. That quantum state that we form as an intermediate, and a little bit of a leftover of the intrinsic fluorescence. But what you're noticing is that like we go back and forth. I mean, we down convert and then we up convert. So we have an equilibrium at any given point in time. And we figured, no, this is not good for, let's say, like a straightforward experiment. And we turned our attention to the absorption spectrum of tetrazine. That's what I'm showing you here. So relative to pentazine, everything is blue shifted, long wavelength absorption at 515 nanometers. And we thought, how about if we filling in a chromophore that absorbs here, so further out in the red, and with that, we do triplet sensitization up conversion. What I have in mind is that I'm taking a phthalocyanine, a palladium phthalocyanine that absorbs at 800 nanometers. The palladium ensures that I'm getting super fast intersystem crossing. So instantaneously, I'm forming a triplet phthalocyanine. And that triplet excited state now can sensitize by triplet energy transfer 1 and 2 tetras. And the 2 tetrasines can upconvert to the fluorescent. And that's been done without ever touching by light any of these tetrasines. If we consider this, there are 2 rate limiting scenarios. One rate limiting is the energy transfer, and the second one is the upconversion, because that energy transfer is molecular, it's concentration dependent, diffusion controlled at best, and the second one is intramolecular, the upconversion. How do you prove that you have the 2 regimes? Well, you do power dependency. In the power dependency, you're not changing concentrations. It's done here for the monomer, the dimer. You're plotting in log, and you see in the low power regime, you see the triplet sensitization as the rate determining step. In the high power regime, you see the up conversion to be the rate determining, because you get 2 consecutive processes, and the slower one is rate determining for the entire sequence. Interesting, if you look at that threshold from 1 to the other, so from a log plot, from a slope of 1 to 2, meaning sensitization as rate determining, up conversion as rate determining, we talk about 3 watts per square centimeter. These are conditions that are doable at any given day, even here at our latitude. The conclusion is simple. We up converting red light into very bright yellow fluorescence of our tetrasines. Quantum yields now are 2% or less than 2%. And I want to just put that in a context, because at the very beginning, I was telling you that at least spin statistically, if I'm taking only the singlets out of all triplets that I can form, there are 9 in total, 5 quintets, 3 triplets, 1 quintet, addressing most likely the singlets, but only with a low quantum yield. At that time, we figured, okay, maybe the bottleneck is the sensitization, and the sensitization is intermolecular. So maybe that is too slow. All right, so we turned our attention to a different approach. This is the palladium that we use, so with a triplet excited state energy of 1.12 electron volt. This is 1.22 if we talk about the ruthenium, and they're both sensitized rubrine with similar up conversion quantum yields. And rubrine is the gold standard, I should say. So how about now doing the following? Rather than using a palladium phthalocyanine, a ruthenium, and rather having an intermolecular, so a concentration-dependent sensitization, followed by a concentration-independent upconversion, integrate them all into one system. And now we got, let's say, everything concentration-independent. But it requires high excitation fluences, because we need in one molecule to excite 1 and 2 of the ruthenium phthalocyanines, spin flipping, triple the energy transfer, then the up conversion. And the challenge is that high fluence, because typically once we run an experiment, we may be exciting only, say, between 10 and 20%. Now that requires 200%. So that's kind of now the comparison. I'm looking at upconverted fluorescence in the case that I'm still going along the same way like before, ruthenium, and I can block that nitrogen or the coordination, and I'm getting that upconverted fluorescence. The all-integrated system has very low upconverted fluorescence continuity. I'm not saying it has zero. I'm trying to be optimistic. There is just a little tiny bit of it. So where is that potential? The potential goes up to 49%. To reach that 49%, definitely you have to go above that 11%, and you have to go above the 2%. So 11% is the spin statistics because of the singlet correlated triplet pair as the rate determining. You can have some spin recycling out of the triplet and the quintet because you're coming in from the opposite end, namely the two triplets. We have currently systems in the lab where we're reaching 30, 35, nearly 40%. So we're not at the optimum of 50%, but still we're making our way. So let me conclude. What I've tried to just demonstrate in a back, and it's like a pardon for maybe being a little too elaborated on the first part on the electron transfer, but I figured that's important in terms of tuning the interaction between, let's say, acenes, whether these are pentascenes or tetrascenes or any other acene that we studied in the literature, by simply finding the right linker, whether that's conjugated, non-conjugated, so saturated or of different lengths. These are aspects on length dependence that I didn't cover at all. What is well understood is the intramolecular singlet fission, so the down conversion, up to 200%. But I'm not saying 200%, but at least up to 190%. There are reports in the literature claiming 200%. We cannot agree with that. And I'm not saying that we cannot agree with what they published in their contributions, but in our particular diamonds. That's because of, let's say, simply maybe rotation, etc. Much more work needs to be done on the intramolecular upconversion. So the triplet sensitization upconversion, your TTA UC. The biggest challenge, however, no matter where you go, down conversion, up conversion, what are you going to do with these triplets? 200% or close to 200%, 11, 20, 30%, whatever, in terms of upconverted fluorescence, in terms of utilizing these triplets and singlets in terms of a photoactive material or even photocatalysis. It certainly requires band alignment or adjustments, but adjustments on both ends. Triplet energies should be tunable, singlets should be tunable, but also the onset of your photoactive material in your solar cell or your solar device should be kind of, let's say, like adjusted to have, let's say, like the optimum conditions. With that said, let's say, like I like to just appreciate the group. There's, let's say, part of it. I don't tweet them. This is, let's say, like a mock-up on one of our excursions last year. But much more important, of course, this is a multidisciplinary, collaborative approach. And what I would like to just particularly emphasize are key collaborations from Rick Tekwinsky. I did mention him already. He's the one that is in charge of the synthesis of all these acenes. There's Tim Clark that helped us a lot with the modeling on something that I skipped in the introduction. So the phenomenon of singlet fission, not like termed singlet fission, is known from, let's say, like the late 60s, early 70s, because there was long-lived excited state determined. So obviously, there's a lot of theory been done over many centuries. So theory is critical. And the other theoretical guru is Michael Toss, who together with Rick, when Rick was here in Erlangen, he was in the physics department in Erlangen, but he moved to the University of Freiburg. And to what I presented, also Mike Wasilewski at Northwestern University in Evanston, Illinois, he has helped us with the time-resolved EPR measurements. And without any further ado, I'd like to just thank you for your attention, and I'm happy to answer and entertain any questions. Thank you.